Right. Good evening, guys. Good morning, good afternoon, depending on the time you'll be watching this video. My name is Molokomi PE. I'm gonna teach you the basic principles of electricity in a revision. Okay. So at first, we have to know what is electricity. We will discuss the electric charge, the electric current, voltage, and resistance, all in Ohm's law, explaining the relationship between all of them. Then we'll look at the power, we'll look at conductors and insulators and electric circuits, series and parallel circuits, okay? Also, and the tolerance in resistance, okay? So we can start now. At first, okay, let me check my pens here. Okay, yeah. So we can start now. At first, what is electricity? Electricity is the flow of electric charge through a conductor. Okay, so we have to know how to define electricity. So electricity, as I stated just now, is the flow of electric charge through a conductor. So what is an electric charge? An electric charge is matter. It's all matter made out of atoms which contain protons, electrons, and neutrons. So electricity is generated from movement of electrons from one place to another. So if you can check a basic example of when you rub a balloon on your hair stands up. This is due to static electricity caused by the movement of the charges, because there's a charge going on. Okay, so now let's move on. Okay, so we will have to define electricity. Electricity is the flow. I'm gonna represent it by an arrow of electric charge. So after this, after you defined electricity, you will have to look at the conductor and insulator. So what is a conductor? And what is an insulator? Okay, a conductor allows current to flow through it, okay, and an insulator does not allow current to flow through it. Does not allow current to flow through it. So an example of a conductor, it's a copper, aluminium, and also water. It's a strong conductor. This one is very dangerous when mixed with electricity. And then you have an insulator, which can be either rubber, plastic, and also glass. So those are conductors and insulators. Some may ask, what is, like, how do birds stand on a live electric wire? So birds stand on a live electric wire because it is covered by an insulator. Normally a copper wire is covered by a plastic insulator, so birds can stay on it without being electrocuted. Okay, I hope that answers that. I'm gonna move on to the three components of electricity. Which is the voltage, the current, and the resistance, which all falls under Ohm's law. So we're gonna look at Ohm's law now. In Ohm's law, you have to learn how to define it. You have to know how to apply the laws, and you have to know how the laws work. So yeah, you can take note of this. Okay. So when we define the term Ohm's law states that, sorry, let me write it in black. Ohm's law states that the current with the unit I is directly proportional to the voltage and inversely, my space is very small, inversely proportional to their resistance. To their resistance. So in simple terms, it can be explained by a formula. It can be explained by a formula which states that V equals to I R, and V equals to the voltage I is the current, and R is the resistance. And the SI unit for voltage is V, current is A for amperes, resistance is ohms. And you can also manipulate the formulas by writing when you're looking for current, it will cost you V over R, and R equals to V over I. So this in simple terms explains the relationship between the voltage, the current, and the resistance. So if you can check here, when you increase the current, the resistance will decrease, and when you increase the resistance, the current will decrease. That's how it normally operates. So this is a short summary that you can know about Ohm's law. And now we go to power. Power is defined as the rate at which electric energy is used or produced. So if you can check, normally in simple English, you can say power is the rate of work. Is what? No, not the rate. Power in simple English, you can say power is the rate at which work is done. So in electricity, we say power is the rate at which electrical energy is used or produced. So those are the difference. There's the difference here, because we're speaking in terms of electricity. We're looking at electrical power, not just power. So power is the rate at which electrical energy is produced or used. So it has a formula, P equals to voltage times current. That's your power. And it's not only this, since voltage equals to current, if you can go up here, you can check voltage. Let me do it in another color. Voltage equals to current times resistance. You can also manipulate the formulas here. So it will be power is equals to current times resistance times current again. So we can say simply equals to I squared times R. And also you can look at I. Let me draw a line here. You can look at I up here. You can manipulate it as V over R. So power will be equals to voltage times open bracket voltage over resistance, which equals to V squared over R. That's all the formulas of power that you can. That's the formulas of pi. So now we are going to look at the conventional current flow. Okay. In the conventional, okay, let me just say this. We have different kinds of current flow. We have the conventional current flow and the electron flow. Sorry, why are my things falling here? Sorry. The conventional current flow is the current flow that flows from positive terminal to a negative terminal. So those are the conventional you can write it properly. Sorry, my handwriting is not as good. Let me just rub here. Conversional. You can just say conversional current flow. So here's the power. And you have the electron flow. The current in the electron flow flows from the negative terminal to the positive terminal. Okay, so those are the current flows. If they say describe the current flow in a circuit, you'll analyze your circuit. If your circuit is like this and the current shown flows this way, it means the circuit has a conventional current flow. Sorry for not writing it in full, guys. You know the handwriting. Conventional current flow. And from negative to positive, if let me just rub you and also show you, it's not fair just to show one. Sorry guys, it's actually not fair. So from the negative terminal to the positive terminal, that's the electron flow. So you must be careful when they ask you a question about the current flow. Okay, so now we are going to look at electric circuits. So before we went to electric circuits, we had to discuss the current flow. So now in electric circuits, we have different kinds of components of which complete a circuit. So a complete circuit has 4 components. I won't say components, it's components. So yeah, sorry about that if I'm misleading you guys. But then if you can check here, yes, if you can check here, if I may draw, I'm using a black one. Okay, just use a black one. In a complete circuit, we have the power source, which can be a battery, which can be okay, we have wires connecting the battery, and we also have, it can be, sorry if my lines are not straight, a cell, a motor, or a bulb, which is the load. And we can also have a switch. Okay, so those are components. Those are components that completes a circuit. Okay, so now we're gonna discuss a fully functional circuit. Okay, the combinations of a circuit. Sorry, in the combinations we have a series, circuit, and it's connected. The components are connected one after another, which is a series circuit. Okay, before I go to a parallel, let me just discuss the series circuit first. Okay, remember on Ohm's law we discussed about the three main components, which are the voltage, the current, and the resistance. Okay, so the voltage will come from this source. Let me just will come from this source. This is the power source, which is it's either a battery or a generator. But then here comes the potential difference, which is the voltage. Okay, so in a series circuit, the voltage is divided, so equals to V1 plus V2. V1 is the voltage at R1 and V2 is the voltage at R2. They divide, they are not the same, but the current is constant. So the total current equals to the current on I1 is also equals to the current on I2. Okay, so this current on I1, this current I1 is the current on resistor 1, and this current on I2 is the current on resistor 2. I hope I'm clear on that. Okay, so from here we'll say, oh, the total resistance, the formula, the resistance are not connected in parallel, so they will add each other, plus R2. Even if there are more than two resistors, you can add another resistors. As long as they are in series, they add. Okay, so now we're gonna look at parallel resistors. Parallel resistors. So resistors connected in parallel. Resistors connected in parallel. Oh, sorry. Yeah, we're gonna look at resistors connected in parallel. Let me just, yeah, from here, let's assume my drawing is not up to scale. I'm sorry for the drawing. Yeah, so resistors connected in parallel. Here is R1, R2, and let's add a battery. Let's add a battery here. So here, okay, you can look. The resistors are connected in parallel. So the voltage across resistor 1 and resistor 2 are the same. So the voltage this time is constant. Voltage at resistor 1 plus voltage at resistor 2. They are constant, they don't change. The current is then divided, current at I1 plus the current at I2. Okay, and the resistance equals to the combination of R1 times R2 all over R1 plus R2. Okay, this is the combinations and the formula, and also resistance can be calculated in 1 over R2 equals to 1 over R1 plus 1 over R2. So this formula can only be applied when you are given two resistors. So you must also consider that. But then for now, you can just compare the two and look at which value is constant on the other side and which value is constant on the other side. Okay, so in a parallel, remember the voltage is in the parallel, the voltage is shared. No, it's not shared. Why did I put this? Sorry, the voltage is equal. It's constant, I mean. In the parallel, the voltage is constant. And in a series combination, the current is constant. So you have to look at those. Then in a parallel, the current is shared. And in a series, the voltage is shared. You see? So yeah, they go like that, and the resistance, it's not constant. Resistor can never be constant. So if you can check in a parallel circuit, when this resistor, when this resistor loses its power or fails, this resistor will still work in a parallel circuit. In a series, if this resistor is affected, this one will also be affected because they are connected in a straight line. It's like those Christmas lights, those old Christmas lights our great grandparents used to use on their trees. So if one is affected, the whole lights are all affected. But then in your house, you can't. A house is an example of a parallel connection. You can't switch off the TV, then the lights also come off. No, that's impossible. So yeah, you must look at those parts. Okay, then we will go to the tolerance. Okay, we'll go to the tolerance. So in basic terms, okay, it falls under the chapter color codes, sorry, but mostly we'll look at the tolerance here. In color codes, let me just let me make the table. I'll pause my video and resume because it's time consuming. Okay, here is my color codes table. In the color codes table, the first color is the first digit, the second color is the second digit, the third color is the multiplier, the fourth color is the tolerance. What is the tolerance? Okay, what is the tolerance? The tolerance is how accurate the resistor value is. It determines the accuracy of the resistor, the tolerance. It gives you the exact value, okay? The exact two numbers or less or one in which the resistor lies between, the most accurate value you can get on the tolerance. So here are the numbers on the table. Black is 0, brown is 1. Sorry, let me just increase my volume here. Thank you. Red is 2, orange 3, yellow 4, green 5. Let me scroll. Blue 6, violet 7, violet, it's violet. Gray is 8, white is 9. So here is a question. Determine the resistance, the accurate resistance using the color codes. Okay, so here I said the first color is the first digit. Here is an example. Here are the colors. So the first color is the first digit, the second color is the second digit, the third color is the multiplier, the fourth color is the tolerance. So here, when you look, when you solve, you will start by saying, okay, you'll start by writing, amen. So, okay, use my pen. Let me use the green one. The first color here is red. So the first color is the first digit. So yeah, red has the digit 2, which is gonna be written here. So let me just increase my screen. 2. Then you go to violet, sorry, which is 7. Then the third color is orange. Orange, remember, it's the multiplier. It's the multiplier. So the multiplier, you're gonna say it will be times 10 to the power. You look for orange on the table. Orange has the unit 3. It will be times 10 to the power of the unit of the color, which is 3. Then plus or minus the tolerance. Remember, the tolerance is the last number. So the tolerance here is gold. So gold is plus minus 5%. That's how the codes will look like. Okay, so from here we'll go to the questions. Okay, so guys, here's the questions. Here's the questions. It's from the previous question papers, one of the previous question papers. So yeah, we have to answer the following questions. So now I want you guys to do number 3.1. You can leave 3.1.2 because I didn't explain that. I'll explain it shortly. Then 3.2 also, yes, you can do it. And 3.3, yes. And 3.3, also 3.4 and 3.5. I'm giving you 10 minutes. You can pause this video for 10 minutes and try do it on your own. Okay. Okay guys, I hope you pause the video and you did the exercises, because now I'm about to answer the following. Okay, we're gonna start at what? Okay, define an insulator. Remember guys, English is not our mother tongue, so when they say define, they mean what is an insulator. How best can you explain an insulator? Okay, so we're gonna define it. Guys, my handwriting won't be as good, so please don't laugh, don't judge me. An insulator, remember, in the start of the video I said an insulator. Okay, let me decrease my to 5. So I said an insulator is a material that does not allow current to flow through it. It's a material that does not that does not allow current to flow through it, or you can say does not allow electrical current, but then you won't be penalized. It's like that. So we come also to the negative temperature coefficient. Okay, I just realized now that, oh yeah, I didn't explain this one to you. So temperature coefficient, actually, temperature coefficient is, how do I define this? How do I put it in simple terms? Okay, temperature coefficient, I would say it's how much the value of an electrical component, like example, a resistor, changes when the temperature changes. So it's in the name actually. So yeah, you can just put it like how I said it. Temperature coefficient is the number that shows how much of an electrical component, like a resistor, example in brackets, when the temperature changes. Okay, so we have a positive coefficient and a negative coefficient. Okay, so a negative coefficient is when the resistance increase when the temperature increases. That's the positive coefficient. And the negative coefficient is the resistance which decrease, okay, the resistance decrease with temperature when temperature increases. I don't know if I'm making sense. Let's say the temperature decreases when there is a rise in temperature. In simple terms, if the temperature increases, the resistance decrease. Okay, that's a negative coefficient. You can just say it's when temperature is inversely proportional to the resistance. Yeah, that's how we put it in scientific terms. So yes, when a negative temperature coefficient is a decrease in systems. Sorry, let me just remember my handwriting. Resistance when temperature in sorry put increases. Okay, that's how you define temperature coefficient. Why am I doing this? Sorry. Yeah, I was struggling in increasing and decreasing my screen. Sorry. So 3.2. Let me write it here. 3.2. State one characteristic of a copper. I think at the start of the video I explained what conductors are and what insulators are and what good conductors are. So copper, I regarded it as a good conductor. If I didn't explain this, sorry guys, my apologies. Copper is a good conductor which allows electricity to flow freely. Okay, sorry about the noise in my background. As you know, We live in households, yo. So yes, you can just state that copper allows electricity to flow easily through it. So it's a good conductor of electricity. Let me, sorry, is a good conductor sorry guys if I'm slow here, my network is bad. Conductor of electricity. So we're gonna look at the 3.3. It says define the term tolerance of a resistor. Remember, I just explained like a few minutes ago that what is a tolerance of a resistor. 3.3. The tolerance of a resistor is the tool that tells us how accurate a resistor value is. Okay, so the tolerance of a resistor is defined as follows. It's a percentage, let me write it here, sorry, is the percentage is the percentage of its resistance sorry, value of how much let me scroll, of how much of how much okay, let me not say how much, let me say how accurate, sorry, I explained it on how accurate. Sorry about the slowness, it's my network guys. How accurate the resistor oh, resistor value is. Okay, that's a short definition of it. Okay, let's move on. 3.4. Sorry. Sorry, I'm having troubles here. Please forgive me. Three point four. 3.4 shows that determine the value of the carbon resistor, which with the following color band, sorry: brown, green, orange, and gold. Okay, so here what we're gonna do, let's write it in full. Brown, green, orange, and gold. So we are gonna look at our, sorry about this, color bonds table. So here on our color bond table, so guys, please copy this table. Please, sorry, yeah, please copy this table so that we can work calculations out properly. Okay, now let's go to our calculations here. I hope you paused and copied the table, because we're now doing calculations. Okay, so brown on our table, the first unit, remember the first color is the first unit, which is brown. On the table it says 1, green on the table it says 5. Then we look at the multiplier. Remember we say times 10 to the power of the number on the multiplier. Orange is times 10 to the power 3. Then the tolerance, plus or minus. Gold on the tolerance table is 5%. Okay, it's 5%. So now, sorry about that. So now we are gonna write it properly. It will be 15,000 ohms plus or minus 5%. So it will be 15 kilo ohms plus or minus 5%. Okay guys, so that's how we are doing things. That's how we do 3.4. okay, the color bond, okay, the color band, sorry. So now we are gonna focus on 3.5. Let me write it this side. 3.5. Let me use the black one this time. 3.5, it says state the Ohm's law. It says state the Ohm's, okay, so state the Ohm's law in words. So you're gonna explain in a summarized version of what is the Ohm's law. Okay, so as we know, according to our knowledge, the Ohm's law explains the relationship between the current, voltage, it explains the relationship between current, voltage, and resistance. Okay, so here, we're gonna say 3.5 Ohm's law. Sorry about that. Let me go back in here. Sorry. We're gonna say Ohm's law. Ohm's law is, let me zoom so that my handwriting can be short and simple. Ohm's law is why isn't it writing? Sorry. Ohm's law is the current in the circuit is directly proportional to the voltage across the circuit. And inversely proportional inversely proportional to the resistance of the circuit. The current of the circuit is the current in the circuit is directly proportional to the voltage in the circuit and inversely proportional to the resistance of the circuit. And remember, all of this happens at constant temperature. Yeah, I finished it here with the dash. So that's the full definition of the Ohm's law in words. Okay, so we'll get Normally it's out of 2 marks. Yeah, I'm surprised they say 3 marks, but then it is how it is. No matter the mark allocation, it doesn't change. Okay, then we go to 3.6. 4.6 says calculate the resistance of a soldering iron heating element that draws a current of 2 amperes when connected across a 220 voltage supply. So here it's straightforward. It's supposed to write 3 marks there. I don't know why they didn't write it. Normally they give 3 or 2 marks. So yeah, you'll be lucky if they give you 3 marks for it. So here you are already given the voltage and the current. So you go straight to the formula. Resistance equals to voltage over current. I remember giving this to you guys. So it will be 220 all over 2, which is our current. Then our resistance will be 110 according to my calculator ohms. Remember to write the SI units, because once you don't write the SI unit, you will be penalized. Okay. Okay, now guys, we are gonna look at 3.7. Okay. So 3.7, we say, sorry about that. 3.7, we study the figure below. Sorry about this. We study the figure below. It shows we have R1, we have R3, we don't have R2, which R1 and R2 are connected in parallel, connected in series with R3. So the parallel combination of R1 and R2 are connected in series with R3. So I total is measured in milliamperes, which milli it will be times 10 to the power negative 3. So we will substitute it as it is. It will be 21,2 times 10 to the power negative 3 on our calculations. Okay, we have the total voltage V, and then yeah, that's all that we have. So okay, and it shows that the current is shared across the parallel combination. So actually you can say IT, let me highlight it, IT is the same as I at R3. Why? Because it's a series combination. So the I total of the parallel combination will be 21,2 milliamperes. Then it will divide across these two resistors. But at 3, again, it will add up, because here the current splits, and comes back here to form 1 again, and go to R3. So it is like that. It doesn't decrease, it doesn't increase. It goes back to normal unless we can remove this resistor. Once we remove this resistor, current will increase. The total current will increase. Okay, let me just, but okay, now let's focus here. on our calculations. So let me just, okay, our first question, 3.7.1, calculate the voltage across R3. Okay. Calculate the voltage across R3. Okay. So going to say V equals to, remember the current at I at R3 equals to the total current. So we're just gonna say IT times with a dot R3. So it will be 21,2 times 10 minus 3. Let me just remove some space here. All in bracket times the dot 470. So you type it in a calculator and you'll get your final answer from there. Let me just do it on my calculator. Okay, we get 9,96 volts. That's our voltage across the R3 resistor. Okay, so 3.7.2. 3.7.2, they say calculate the voltage drop across R1. Remember, the voltage drop across R1 equals to the voltage drop across R2. So we're looking for the V parallel. So V, okay, let me just remember V parallel is connected in series with R3. So it will be the V total equals to the V parallel plus V at R3. Okay, so we are gonna manipulate our formulas and to say VP equals VT minus VR3 so VT is 12 minus the voltage across R3 is 9,96, which will equal to, according to my calculator, 2,04 volts. Okay, that's the voltage across R1, which is the voltage across R2, which is the voltage across the parallel. Okay, get 3.7.3. Okay, so calculate the current through R1. So we have the voltage flowing through R1 and we have the value of the resistor 1, which is 220 ohms. then we calculate the value of I1. Okay, so the current of I1 will be, okay, let's say, oh sorry, yeah, let me just click my pen. I keep forgetting my pen, sorry guys. 3.7.3 3.7.3 I equals to V over R. Remember, we're looking for the current across R1, so here it's gonna be still the same voltage across R1. So since we just got the voltage across R1 on top, it's gonna 2 comma 0 4 over 220, which is gonna be 9 comma 2 5 times 10 to the power negative 3. Sorry about my handwriting, guys. Which equals to 9 comma 2 5 milliamperes. So that's our current across R1. Okay, is it? Now we are looking at 3.7.4. Okay, so here at 3.7.4, we are going to calculate the current through resistor 2. Remember the formula of, okay, the current, okay, let me just show you here. Remember the current splits on I1 and I2 across the resistors on the parallel combination. So we have the total current and we have the current flowing through I1. We have I1, okay? So what we're gonna do now, is that we are going to utilize the formula from the parallel combinations of is it IT equals to I1 plus I2. So we manipulate the formulas. I2 equals to I total minus I1. Okay, so I total is 21 comma 2 minus 9 comma 25, sorry, that's 2. So someone will ask, why didn't you convert this time? Because they are all in milliamperes, so there's no need for me to convert. They are all in the same units. So my answer, according to my calculator, will be 11,95 amperes. I hope I'm clear here, guys. I hope you understand here. Now we are going to look at the value of R2. So remember, at first we were looking for the voltage drop across R1, and I told you that the voltage drop across R1 equals to the voltage drop across R2, and we have the current flowing through R2 just now. So we can just go and play with our formulas, because we're looking for R2. We have the voltage across R2 and the current across R2. Okay, so the voltage across R2 is the voltage across R1 because of the parallel combination between them. Okay, so what we're gonna do now, let me click my beloved pen. My pen, why isn't it clicking? Okay, just okay. Now it's confusing me. Oh yeah, now I clicked my pen. It will be R2 equals to V at R2 over I R2. Okay, so it's gonna be 2,04, which is our voltage at R2, over 11,95 times, oh, this thing is slow, sorry guys, times 10 to the power -3. Then someone asks me that why do we convert now? Now we are converting because we are looking for an exact value of the resistor. So we are converting it to its actual units measured in amperes, not milliamperes. So we have to times it by 10 to the power -3, the current. Remember here, I didn't convert because all the units were in milliamperes. So now, what I'm gonna do is divide 2,04 times by 11,95 times 10 to the power -3, which is gonna give me 170 ohms. Okay, then we move on to the last question. Last question is 3,8. Explain what will happen to the total current if R3 is removed. So here, what we're gonna do Yes, what will happen to the total current in figure 3.7 if R3 is removed? So this one I'm not gonna write it, but I explained it when I was interpreting the circuit, that when R3 is removed, the total current will increase. Because why? Because the resistance of the circuit has decreased. Reason being, remember, on according to our laws, the current is inversely proportional to the resistance. So an increase in current will decrease the resistance. So now in this point we are decreasing the total resistance. So the total current will increase. I hope we are clear on 3.8. I'm not gonna write it, I just explained to you guys. So thank you for this video. Take care. I hope you will do well. I hope you understood me well.